I would say that this is a sort of a survey talk. I'm not actively working on this topic currently, but this is something that I got fascinated quite recently, and I wanted to uh, make this opportunity to, to share this wonderful topic with everyone around the world, especially young researchers. So, and I think the organizer did a wonderful job of ordering the talks because Seunghoon, the previous talk of Seunghoon is related to this topic that I'm going to present. And yes, this will make things convenient, sort of, for me. So I guess I should say thank you. Okay, so let's start. Uh, Today I'm going to be talking about, just like the title says, convex projective deformations of especially three manifolds, and especially more specifically, hyperbolic manifolds that has cusps. So let's just quickly review what happens in dimension 2 when we have surfaces. Deformation theory of complete hyperbolic structures on a surface of finite type with negative Euler characteristic with finite volume is very well known, and it is called the Teichmüller space. When there's a typo here. It is homeomorphic to Euclidean space of this dimension. And here G is the genus of the surface and B is the number of punctures or boundary components. But in higher dimension, this good picture, this wonderful picture does not happen because we have Mostow-Prasad rigidity. If we have two lattices in PON1, where n is at least 3, and they are isomorphic, then in fact, these two are conjugates in this group. So in the terminology of deformation spaces, this Teichmüller space of such structures is just a singleton, so no fun. Luckily, the situation for deformation theory of real projective structures in higher dimension can be much more flexible than this. And some aspects of this theory was explained previously by Seunghoon wonderfully. And also among such structures, convex projective structures have nice geometric description, which resembles that of complete hyperbolic structures. So that will be what I'm going to talk about here. So yes, this we already saw in the previous talk, but let's just quickly review. An affine chart is a subset of n-dimensional real projective space, and it's just nothing but the complement of a hyperplane. And we say that a subset omega in a projective n space is properly convex if its closure is compact and convex in some affine chart. And the properly convex subset is, moreover, in addition, is said to be strictly convex if the boundary of the subset does not contain any non-trivial line segment. So I have some examples just to give you some pictures in mind. Rn embedded in Rpn via the map, this map we very well know, will give an affine chart of this n-dimensional real projective space, and the Klein model, projective model of the hyperbolic n space gives an example of strictly convex subset of Rpn because it's a disk. And here's just very elementary example. Let's consider a disk folded in half with yes, let's just say a disk folded in half. Then this will give a properly but not strictly convex subset. And whenever we have this kind of subset, then we can consider the group of matrices that preserves this particular subset, and we will call this group the automorphism group of omega. And from now on, we will denote omega will always denote a properly convex open subset of RPN. And whenever we have such a subset and a discrete subgroup lambda of PGL omega, then the quotient the quotient of omega by lambda will be a manifold, because this group being a discrete subgroup is equivalent to the group acting on omega properly discontinuously. So we call such a manifold a properly convex projective N manifold. It's a long name, so we will not say properly. We'll just call it convex projective N manifold in this talk. Then, of course, we want to think about sort of moduli space of structures. So let's fix an N manifold M with we'll assume that it does not have any boundaries, because when we have a boundary, any boundary components, then it is known that we can consider any geometric structure on such manifold as a restriction of a structure given on a defined on a thickening of such manifold. So we will always assume that we do not have any boundary. And let's assume that G is, oh yeah, from now on, we'll denote this projective general linear group as G, and gamma will denote the fundamental group of the manifold. Then this smooth manifold we say that the manifold has a properly, again, it will be omitted soon, but properly convex projective structure if we have a pair of a representation from gamma to G, say rho, and a map delta defined on the universal cover of M and mapped into RPN, which is a rho equivalent diffeomorphism onto some properly convex open subset omega of RPN. Here, delta will be called a developing map of the structure, and rho will be called a holonomial representation of the structure. And this rho is always discrete and faithful because we have a condition that delta is a diffeomorphism, and its image is the image of delta is a properly convex open subset. So this also implies that we have discrete faithful representation rho, and delta also descends to a diffeomorphism, which we will denote by delta bar, and it's a diffeomorphism between the original manifold M and a convex projective manifold of this form. So it's just basically analogy. You can see the analogy between the definition of Teichmüller space and this version. So we can now define the space. Here I have a question mark because I will not mention what kind of topology we endow with this set. But let's just say, believe me, let's just say we have a space. So the space of convex projective structures on M is the set of such pairs, delta comma rho, quotiented by an equivalence relation where two such pairs are equivalent if there exists an element G, small g, in the group G, such that relates the pairs in this way. Here, the dot means conjugation. Conjugation by G in the homomorphism representation variety. And the deformation space of convex projective structures on M is, again, the space of such structures quotiented, again, by an equivalence relation where we have two structures equivalent if and only if there is a diffeomorphism of M, which is isotopic to the identity, so that the developing maps can be related this way. Oh, I think I here missed. There exists phi and there exists a small g in G such that this equation holds for some lift phi tilde of phi. So this is just really a parallel description of something you expect from the definition of Teichmüller space. And yes, as I explained before, we have good topologies. So we have a deformation space. And then as you can see, we also have another data, which is a map defined on the deformation space of such structures to the character variety, where the character variety is the representation variety quotient by G action by conjugation. Then we have a natural map, which we will just call holonomy map. For each structure or the point in the deformation space, you just assign it to the class of its holonomy representation. This is well defined. And when our manifold M is compact and hyperbolic, this deformation space contains a point, a distinguished point that comes from the unique complete hyperbolic structure on M. Let's denote the holonomy of hyperbolic structure on M by rho hype and its composition with the inclusion map by rho hype also. Then the work of Koszul is that this holonomy map is in fact a continuous and open map. Because it's an open map, if you want to realize, if you want to construct some convex projective structures on a hyperbolic manifold, what you can do is you don't work with structures, but which are geometric data. You descend to the space of representations or the character variety, and you deform the representation, holonomy representation slightly. Then because this holonomy map is an open map, you will always have representations which are also holonomy representations of some convex projective structures on M. But unfortunately, this breaks down when M is not compact. In other words, when we have a cusped complete hyperbolic manifolds. Because this happens because of the hyperbolic den-filling theorem of Thurston. We have sequences of holonomies of incomplete hyperbolic structures that converges to rho hype. But as I mentioned before, holonomy representations of convex projective structures should be discrete and faithful, but these sequences always give us non-discrete faithful representations, so they never correspond to a convex projective structures, and hence this map cannot be open when M is not compact. And one might guess that this failure comes from the weird geometry of the ends. So Cooper, Long, Tillman worked on this to give a sufficient condition to, I would say a relative version of this principle. And yeah, they succeeded. So when we have a non-compact convex projective manifold M with certain specific ends that are called generalized cusps, this I will define soon, then we have a sufficient condition to obtain some holonomy representations of convex projective structures by deforming the initial holonomy. Let's say we have rho, which is the holonomial representation for the initial structure, and you choose rho prime, which is another representation sufficiently close to the initial one. And let's assume that this new representation restricted to each of the end of the manifold is the holonomial of some generalized cusps for each end C of M. Then this new representation rho prime is also the holonomial of some convex projective structure. In other words, if we deform the initial holonomy so that the ends continue to be generalized cusps, whatever they are, then the result is still the holonomy of some convex projective structure. And moreover, we have this another theorem by Cooper and Tillman. Let's say we have a convex projective manifold, and of course, it is not always true that the ends of a convex projective manifold is a generalized cusp. But when we have these fairly nice algebraic conditions, then the end, any end of M is indeed a generalized cusp. But what we should note here is that these three conditions will automatically hold when we assume that M is a complete hyperbolic manifold of finite volume, because these properties are what you can expect from cusps in such manifolds, hyperbolic manifolds. So whenever we try to understand the deformation space of convex projective structures of a complete hyperbolic manifold, we have a distinguished point, and moreover, we know what specific ends will appear in such deformations. So people were really intrigued by this and tried to understand what generalized cusps are, how they are classified, or how we can achieve them by deforming hyperbolic manifold. I think I should be a little bit faster. So just like we do in hyperbolic geometry, an element small g of G that preserve a properly convex domain omega can be classified into three classes. It is elliptic if it fixes something, some point in omega. It is parabolic if it acts freely on omega, and every eigenvalue of A has modulus 1, and hyperbolic otherwise. What Cooper, Long, Tillman found out for strictly convex projective manifolds is that they always admit thick thin decompositions, and moreover, their thin part is diffeomorphic to the product manifold of an infinite interval and its boundary, and each end must have each component of the thin part must have virtually nilpotent holonomy, and any non-trivial elements of this image is either all parabolic or all hyperbolic. When it's all parabolic, we have something called cusp, which is really projectively equivalent to the cusps in hyperbolic manifolds. This theorem motivates the following definition, which is the definition of generalized cusp. A generalized cusp is a convex projective manifold satisfying the following. It has virtually nilpotent fundamental group. Its boundary is compact and strictly convex, and the manifold is diffeomorphic to the product of its boundary and infinite half interval. What Ballas, Cooper, Leitner found out is that this rather complicated definition can be replaced with a very concrete objects. That is, a generalized cusp is always projectively equivalent to some cusp of some type. I will informally call them model cusps here. And each model cusp has an integer which describes its type. So the main topic, the thing I want to mention here is the structure of model cusps and their domains. To understand that, we need to revisit hyperbolic space, and let's be quick. We have a quadratic form of signature n comma 1, specifically this one, on Rn plus 1. Then the projectivization of its negative cone is the paraboloid model of hyperbolic space, and it can be written in some specific affine chart. It can be written this way. So in fact, it is the inverse image of some smooth, strictly convex function, and its horospheres centered at this particular boundary point is of the form H inverse C. That is, it's the level set of this function H. And lastly, the group of parabolic translations in this Lie group, which is the isometry group of Hn, is written as very explicitly this way. It's a unipotent matrix, and this, we know that this group acts simply transitively on each horosphere centered at the infinity. Now we're gonna just mimic this construction, this feature, to define model generalized cusps. Let's say we have an integer k, which is at least 0, and in fact, it can be exactly n, but in this talk, I'm not gonna explain that type. So let's say k is smaller than n. Then the model cusp domain of type k is omega k, and it's the inverse image of some function hk in Rn, where the hk is defined this way. So the difference is that the bigger the type gets, the more logarithmic terms appear in the formula for the function, and we have less quadratic terms. And a horosphere in this domain will be any subset of the form hk inverse c for some negative number c. So this is, again, you can all again see the parallelism. And each omega k is preserved by this group, which we will call the translation group of type k. Here, what you can notice is that the bigger the type gets, k gets, we have the unipotent block gets smaller, and we have more diagonal terms. Yes, the motivation behind this construction is that in strictly convex case, we have that the holonomy of a thin part should always be consist of parabolic elements, and the parabolic elements are always unipotent or conjugate to unipotent matrices. So to obtain something non-hyperbolic, we just add more blocks with diagonal terms, which gives some actions in a hyperbolic way. That's the motivation behind this definition. And what Ballas, Cooper, and Leitner found out is that, in fact, this domain alone has the product structure, and this group is isomorphic as Lie groups to Rn minus 1, and it is a subset of a subgroup of PGL omega k. So it preserves omega k. Moreover, the tk acts simply transitively on each horospheres in omega k. So this group tk is really the translation group, sort of, which behaves exactly the same way as the parabolic translations would in Hn. And whenever we have a lattice in Rn minus 1, we can map it into the discrete subgroup of tk, and then we can obtain a convex projective manifold omega k quotient by lambda, and such a manifold will be called a model cusp of type k. Here are some pictures I drew myself so that I can give you some figures in mind, especially in dimension 2. This is the type 0. On the leftmost side, we have the type 0 domain. It's nothing but in an affine view, it's just an epigraph of a quadratic function. And in the projective view, we have a unit disk. And the type 1 domain will be the epigraph of a logarithmic function. And we have the projective view here. And when it's type 2, then we have the epigraph of a function, something like y is 1 over x. And model cusps domains in dimension 3 can also be, you can also imagine them with these figures in mind. Yes, so these are very interesting ends that appear when you try to understand convex projective deformation of hyperbolic, cusped hyperbolic manifolds. And I will give you one example, but I'm running out of time, so I guess I cannot explain all the details of the construction. And I'm sorry, I will just I'll just assume that we all know what bending constructions are. You can always deform a hyperbolic three manifold along an embedded totally geodesic surface sigma, if there is any, and the resulting structures are called bending of M along sigma. And in fact, we have one parameter family of deformation, and Johnson and Milson found out that these deformation gives projective structures that are never hyperbolic except at the initial structure. And what Marquis found out in 2012 is that, in fact, each projective structure obtained by bending is in fact convex projective structure. And what Ballas-Marquis found out is that by performing bending, the types of generalized cusps you can obtain are always of either type 0 or type 1. Nothing else happens. And it is of type 1 if and only if certain homology class is non-trivial. This is fairly easy. This gives us a fairly easy way to check. And Vallas and Marquis, in fact, found out that the Whitehead link complement does obtain convex projective structure with one cusp of type 0 and the other cusp of type 1 by observing the homology class. Yes, there was one more thing I wanted to mention, which is related to how people are working on now, currently, but I do not have enough time. I already spent a lot of time, so I guess I will stop here, and thank you for your attention.